Center for Computational Quantum Physics at the Flatiron Institute, 23rd Street, I think. Wow.
21st, yeah.
Simultaneously, he's got the chair in condensed-matter physics at the Collège de France. He's also professor of physics at École Polytechnique.
Well, I'm on leave from that.
What?
I'm on leave from that.
Okay, fine. Actually, the most interesting thing is when you look them up on Wikipedia.
Oh yeah, I know.
Off,
oh God.
George's passion for science began during his teenage years at his father's laboratory, where he used to capture mice for his father's experiments at the French Institute of Health and Medical Research.
Well, this is true.
I mean, maybe if you look around today during the talk,
I could find one. I have no idea who wrote that, by the way.
Right. He has worked for very distinguished people. His degree is from École Polytechnique with Pierre-Gilles Dejean. He then became a postdoc at Princeton with Phil Anderson, which is where I met him first, and then moved to Rutgers, where with Gabe Cochlear, he developed dynamical mean field theory. He's got many awards, among them the Condensed-Matter Europhysics Prize, the Médaille d'Argent, the CNRS, and the Hamburg Prize for Theoretical Physics. And today he's going to tell us about quantum matter with strong correlations.
Okay, thank you so much, Paul. So, you know, this is the danger of Wikipedia pages, because part of this information is actually not entirely correct. I was never at Rutgers working with Gaby Cochlear as a postdoc, but it doesn't matter, you know. Yeah. But of course, we did a lot of work together. Anyhow, it's a real pleasure to be here. And I'm very happy to be a little bit more permanently in New York. And as of today, actually, I can, you know, I'm legal here. I just got this, this NYU affiliate position. So I have my badge, I'm legal. Great. Okay, so basically, the title of my talk, as you see here, is about quantum matter with strong correlations. And since I understand this is a sort of a broad audience colloquium, I thought I would devote at least the beginning of the talk to explain, you know, what the hell this is, you know, what do we mean by strong electronic correlations, and especially which materials display such correlations, and especially why they are interesting, why do we care about such materials. So I would like to start the talk by giving you some sort of broad overview of the field, and, you know, perhaps later down into the talk, we'll go into somewhat more concrete problems. Okay, so if we are talking about materials, as you will see in the talk, there are different forms of quantum matter that display strong correlations, but I will start with electrons in solids, and especially, you know, solid-state form of materials that actually display such phenomena. And so what are the suspect materials? Basically, these are the ones in which we have localized orbitals. So in many, many solids, the electrons are very delocalized, the orbitals are very extended, and as a result of this, kinetic energy basically dominates everything, especially because the screening considerably reduces the strength of the interactions. But there is a whole family of materials in which kinetic energy and on-site interactions actually compete on equal footing. And this occurs obviously when you have electrons that are close to the Fermi level, so which are low energy electrons, but which live in orbitals which are spatially localized. And
what scales?
What do you mean what scales? Spatially localized on what scales? Okay, so you know, the answer to your question is here. If we actually look into very simple atomic physics reasons, if we're going to look at the 4s shell, let's say, of transition metal, for example, this 4s shell is going to be very extended because the radial wave function has to have nodes, right, just to ensure orthogonality with the lower, same angular quantum number, but lower rank, right?
These
but
are all
this is just for the hydrogen atom. These are just probably densities for the hydrogen atom. That's all there is to it, right? Just for a simple atom.
And this spatial scale.
Yeah, so it's just a few Bohr, it's just, yeah, Bohr radii. So, you know, the guys I'm particularly interested in here, for example, are the d states with L equal 2 in transition metals, because, of course, if we start populating the 3D shell, as in a transition metal, there are no shells with lower principal quantum number and with the same value of L equal 2. These things just don't exist. So this is why the radial wave function does not need to have a 0, and hence these wave functions are fairly localized around the atom. So this is really atomic physics 101. And so it immediately tells you that the suspects for having rather localized electrons in solids are compounds which will contain transition metals, especially of the 3D row, but there is also very interesting physics with transition metals for from the 4D row and also 5D row, and even more so, materials that would contain rare earth, because the 4f orbitals of a rare earth are extremely localized around the atoms. And to some extent also the 5f with actinides. So, you know, transition metals, rare earth and their compounds, like oxides of transition metals, rare earth and actinides and their compounds are obvious candidates in which these effects will be important, and also molecular solids, because in molecular solids we have molecular orbitals which overlap relatively little from one molecule to the other, just because the lattice spacing is fairly big. These are sizable molecules, okay? So I would say the field of materials with strong electron correlations is pretty much covered by transition metal oxides, transition metals, rare earth, actinides and their compounds, and many molecular solids.
So when you say localized, you mean on the scale of the
on the scale of the interatomic spacing. You know, I just mean that the overlap of two neighboring wave functions is relatively small. So just to be more quantitative, the transfer integral that you would estimate by the overlap of two neighboring orbitals is comparable to the on-site screened Coulomb interaction. They both are typically on the scale of a few eV, you know. While if you take silicon, right, you're going to have bandwidth that are large, and this on-site screen interaction would be a much smaller scale than that. So that's the general concept. Okay, so the thing I want to show you just a little bit on the phenomenology side is that these materials actually do interesting things. And this goes to all the way to, you know, very old topics that were studied many, many decades ago, such as metal insulator transitions in multi-insulators and so on, all the way to more modern topics. And I'm just going to show you a few examples. So this sort of illustrates the kind of materials we are talking about. There is like the, you know, very old-fashioned things like iron oxide, rust, okay? All the way to being able to fabricate these transition metal oxides in a much more controlled way, admittedly, than this stuff, namely being able to elaborate well-controlled heterostructures of these oxides, basically atomic layer per atomic layer. And one of the beautiful things that has been happening in this field in the last 10, 15 years or so is the capacity of fabricating artificial structures made out of such materials or combinations of these materials with standards that are comparable to what you can do with semiconductor physics. And, you know, at the CQP here, there is a facility being built to actually do MBE on some of these materials and other elaboration methods. Okay, so let me show you some examples of these phenomena. So there are some really time-honored ones, like I'm sure Pierre remembers from the good old days of Bell Labs, right, where people were interested in the phase transitions of V2O3. So V2O3 is one of the oxides of vanadium, and it displays a very interesting phase diagram as a function of temperature and pressure in which we have different phases. So here at low pressure, we have a phase which is an insulator with local moments, but no Lagrange order if we look at them at sufficiently high temperature. And if we pressurize the system, it can go into a metallic phase through a transition which is first order, very sharp, and ends here into a second order critical endpoint, a little bit like a liquid gas transition. Of course, if we continue cooling down this system, then it becomes an ordered insulator, you know, in which all these spins that fluctuate here will eventually order into an antiferromagnet. This kind of physics with like three phases, paramagnetic insulator, a paramagnetic metal, and an antiferromagnetic insulator, is also found pretty much in the same manner in some of the organic conductors I alluded to in the introduction, where you have here a first order transition between two similar phases, and here it's even prettier because this metal actually wants to become a superconductor below a transition temperature which is only about 14 Kelvin, but which by the standards of the typical energy scales in this system is pretty high Tc. Okay, so these metal insulator transitions are not only interesting to theorists, but they're actually also interesting for practical applications. This is another of the vanadium oxides, vanadium dioxide, and this guy has the good taste of having a metal insulator transition just at about room temperature, at about 20 Celsius, so that you can actually switch it from being metallic above 20 C to an insulator below, and you can actually use it to coat windows that would let the infrared come in when it's cold outside and not let it in when it's hot outside. So people call these intelligent windows. I'm not completely sure that just switching between two states is a good definition of being intelligent, but anyway, for a window, it's maybe okay. So that's an example of practical applications of such metal insulator transitions. And you know, I could go on and on with such examples. This is another set of materials which are transition metal oxides, rare earth nickel oxides, in which actually this metal insulator transition here can be controlled in terms of what is the transition temperature over a very wide range by either doing substitutions on the rare earth site or by applying strain and so on. You'll see more of this in the rest of the talk. Okay, so these were MITs. I'm sure here I have more examples. Of course, it would be impossible to talk about this field without mentioning the class of materials that have really put materials with strong electron correlations back under the limelight in the late 80s. And these are high Tc superconductors. This is not going to be a talk about high Tc superconductors, but I'll sometimes mention them. So you know very well that around 1986 there was a real revolution in the field of superconductivity, in which all of a sudden the transition temperature of known superconductors increased by a huge jump over a period of just a few months, and a new family of materials were discovered, all based on copper oxides, in which the transition temperature can easily overcome liquid nitrogen. So there was a considerable revolution in the field, and it also emphasized the fact that our understanding of strong correlation between electrons in solid at that time was actually pretty poor. Some of the concepts were there, but certainly many of the, on the theory side, for example, many of the theoretical tools that we need to make more quantitative calculations or predictions about these materials were lacking. And one of my research agenda over the last 20, 25 years has been actually to develop such tools. Okay, the ITC problem, ITC superconductor problem, is still to a large extent a field of active work by many theorists or experimentalists. And my point of view on this is that many of the mysteries of this field have actually been gradually clarified. There's been an enormous amount of progress from the point of view of experiments. There have been also significant progress from the point of view of theory. But of course, there are still some open problems. It's a very challenging problem for condensed matter physics. Okay, I already mentioned those guys. Other examples of interesting superconductors, again, among the organics, which are also systems in which electron-electron interactions are very important, are the fullerenes. There are very few people who actually are working on fullerenes these days, even though the field has been recently sort of rejuvenated by the discovery of the enhancement of superconductivity by by laser pumps, which I will perhaps mention at the very end of the talk. Okay, so basically, you know, after this little overview of what materials we are talking about, I'd like just to summarize the take-home message. These are systems which exhibit many competing phases. We've seen these complex phase diagrams. There are even more complex ones that I didn't show you. These, you know, hints at small energy differences between the different phases, which raises, you know, which offers the possibility of trying to drive the system into one phase or the other if you want to achieve a given functionality, but also raises an issue as to how to stabilize the system in a given phase. So controlling these materials is really very much on the map. And there's been new techniques to do that have been developed in the recent years. And the fact that there is many competing phases has also a lot to do with the fact that there are many degrees of freedom which are competing one with the other. We have charge, spin, lattice degrees of freedom, orbital degrees of freedom. So it's a very complex multi-degree of freedom problem. Okay, so just to give a general overview of what's important in the field, in my opinion, the keys to success to any, you know, research enterprise in this field is actually to combine together three things. Of course, everything relies on discovering new materials with interesting functionalities and elaborating them with more and more control and being able to synthesize materials that combine different functionalities. So it all relies on material science and chemistry, solid-state chemistry in particular. Then, of course, we need experimental techniques to investigate the fundamental physics in these systems. And if you look at the ITC superconductivity problem, you could make a claim that basically every single technique in condensed matter physics has been pushed to a much higher degree of perfection and accuracy, triggered by the fundamental interest in the cuprates. And this is the case of angular resolved photoemission spectroscopy, of STM, of many other probes that were in a very different state 20 years or 25 years ago when this problem appeared. And of course, theory, I claim, has also some relevance, even though very often it comes to explain some of the observations of either the chemist or the experimental physicist. But as you will see later in the talk, I hope, there's been quite a bit of progress in being able to say even quantitative things on these systems by developing appropriate methods. Okay, so since I just talked about theory, let me try to give you an idea of why these problems are actually very challenging from the theoretical point of view. And to do that, I would like to basically go back to the basics. we have a bunch of interacting fermions. So we have a solid in which we have electrons floating around the atoms, and these electrons strongly interact one with the other, and they are fermions. So why are interacting fermions intrinsically a complicated problem, a hard problem? Well, there is something which is common to all assembly of a large number of quantum degrees of freedom, which is the fact that the Hilbert space is exponentially large. So if you just take a small piece of matter, you'll have something like 10 to the 21, 10 to the 23 particles or electrons, and the Hilbert space is actually exponential of this, okay? So don't even think of diagonalizing the Hamiltonian. With the most powerful computer in the world, you can probably diagonalize 20 particles, certainly not 10 to the 21. Okay, shall we try to close the door? So, attacking this problem by brute force diagonalization of the Hamiltonian is just not going to be possible. And yes, Moore's law, allow you to do one more particle every 18 months, but that's going to take a long time before you reach 10 to the 21, right? So just the sheer increase of computer power is not going to do the job. So this is a very beautiful example in which developing computational techniques to handle this problem does not mean brute force simulation and just going home and reading the answer on your computer. If you are going to go at this problem with computational methods, you actually need to view computers as a way to investigate matter, to understand what's going on, but not as just a simulation machine. And in fact, all the progress in this field has been achieved, A, by devising new methods and new theoretical concepts to think about the problem, and B, by devising new algorithms that allow to, to a certain extent, understand these systems beyond the simple increase of computer power. Okay, so this would be common to bosonic and fermionic problems, right? Bosons have even larger Hilbert spaces, for that matter. So what makes fermions so difficult? Well, what makes fermion difficult is that if we try to attack these problems with other kind of algorithms like quantum Monte Carlo algorithms, that works very nicely for bosons because the quantum amplitudes for a bosonic system, except in some special cases, have mostly positive signs. While if you actually do that with fermions, and this is something which is well known, of course, also of people who do lattice gauge theories, for example, you get a sum of sign, a sum of amplitudes which are alternating in sign. This is the so-called minus sign fermion problem. And below a certain temperature, the system just becomes uncontrollable. So it's the size, the sheer size of the Hilbert space plus this question of alternating signs in fermionic amplitudes that makes the problem very hard computationally. So this was actually very nicely expressed all the way back, not exactly in those terms, obviously, but very many decades back by Paul Dirac. There is a famous article of 1929 by Dirac, which is entitled Quantum Mechanics of Many Electron Systems, very crisp title. And Dirac wrote this sentence saying that basically, this is 1929, all the basic principles of quantum mechanics are now understood, and the underlying physical laws which are necessary to understand most of physics and all of chemistry are known. So that the only difficulty, he said, is that the exact application of these laws leads to equations much too complicated to be soluble. So, this sentence by Dirac was often seen as an extremely arrogant sentence that, okay, we're going to predict DNA from first principle because we know quantum mechanics. So that sounds a very reductionist view of science, a little bit like, this joke here that, is basically introducing some sort of hierarchy among the different sciences. Of course, the ultimate one being mathematics. which is even above God. But this is, in my opinion, a complete misconception of misinterpretation of Dirac's sentence. People who quote this sentence as a sign of the arrogance of theoretical physicists miss the second sentence, which follows that sentence immediately in the same paper. And Dirac wrote this very modest one, just as the next sentence. He said, you know, it therefore becomes desirable that approximate practical methods, so he was well aware that we are not going to diagonalize a Hamiltonian with a 10 to the 23 sized, with 10 to the 23 particles. So we should devise approximate practical methods of applying quantum mechanics to large systems, he meant, which can lead to an explanation of the main features of complex atomic systems without too much computation. So this sentence is really a programmatic sentence, even today, even as of today, except that, you know, without too much computation doesn't exactly have the same meaning in 1929 and now. You know, I think probably what Dirac meant by without too much computation meant that something that he, Dirac, can do in about a month with a pencil and a pad of paper. Okay? Now, the way I would interpret this sentence is with putting to good use everything that we've learned and we are still learning about algorithmic developments and the power of computers. But you know, with this generous interpretation, I think we can say that this sentence is still a programmatic sentence for anybody trying to make progress on this general class of problems of many interacting quantum particles. Okay. In fact, you know, Paul mentioned that I'm now setting up a new institute in New York, and I'm going to, you know, I thought maybe you would be curious about what this new institute is about, so I'm going to show you a few slides about that. And this last sentence by Dirac is just a perfect agenda for what we want to do in this research center. So I'll just take this for all practical purpose as a sort of somewhat vague but broadly defined agenda about what we want to do.
Did you say it was problematic or programmatic?
Programmatic.
Programmatic.
If I say problematic, it's also problematic actually, but
right, and that's agenda in terms of programming.
yeah, this is what I mean.
Right.
This could serve as a perfect definition of our scientific agenda. Yeah, that's what I mean. Okay. So let me tell you a little bit more, just in a few slides before we go back to science, about this center. So this center is not just one center. It's actually part of a whole institute. And the idea is to create an institute in which a bunch of scientists would be gathered who all have an interest, a taste, or a special expertise in computational methods and the development of such computational methods for different fields of science, not only just applying these methods to different fields of science, but really pushing the frontier of the methods and of the power of the methods to these different fields. And the idea behind this institute is to have 4 research centers. They will all be physically located in the same building, which is going to be a 12-story building. At the top of the building is, of course, quantum physics, you know, obviously. Huh? No, well, at the top of the building is lunch, okay? That's the 11th floor. Then we have quantum physics. We have to have things in order, right? Then we have biology, surprisingly. I would have put astrophysics there, but we have biology. And we have astrophysics, and then we have something else, which we don't know what it's going to be yet, and we are talking about it. So right now, the Center for Computational Biology, which has been created about 3 years ago by Leslie Greengard, who is, of course, former director of Courant, is already up and running. It has about 50 people, so it's already more or less full house. The Center for Computational Astrophysics was created about a little more than a year ago, and it's headed by David Spergel, who is a Princeton professor and famous astrophysicist, and it's already in very good shape. And we are starting the third one, the Center for Computational Quantum Physics, which is just open shop just about a month ago. And it starts with a small nucleus of about 8 to 10 people, but we're going to grow slowly with quality in mind, but steadily, hopefully. And if you want to see the gentleman who is actually funding the whole operation, here he is. This is Jim Simons and his wife Marion Simons here, who on the day of the opening of this whole institute, the official opening, which was just about a month ago, cut the ribbon of this new institute. So the idea is to have in a single place scientists and software developers and programmers and computer scientists who can share their expertise in the techniques, but who are primarily scientists interested in biology or astrophysics or materials and quantum system or whatever the topic of the fourth center will be, and develop specific methods aimed at these fields. So that's the general concept of what we are trying to set up very close to here in New York. Okay, so actually at this stage, before going back to the scientific main thrust of the talk, if there are questions about what we are planning to do or not planning to do, I'll be happy to answer. Okay, we can take the questions at the end as well. Okay, so as far as the center I'm leading together with Andy Billis is concerned, what we want to do is to be focused on methods. We want to develop concept theories and algorithms to actually make progress on the Quantum Mony-Electron or Fermion problem with a long-term perspective. So, we can be very complementary to more grant-driven programs that will attack similar problems, but with a more short-term agenda, and hopefully work in synergy with, for example, DOE centers that have been created to work on material science problems. We want to cover actually a very broad range of methods, so I'm not going to enter into the details, and understand problems at equilibrium and out of equilibrium, which is highly motivated these days by pump probe experiments and some free electron laser coming online and so on.
Could you just say what these acronyms are?
Yeah. So Pierre. So maybe, with all due respect, I'll do this a little bit later in the talk because I want to get back into science. But à tout seigneur, tout honneur, and I should of course mention that DFT means density functional theory, which probably needs not to be introduced here, since Pierre is one of the founding father of this approach. And I will explain, hopefully at some point in the rest of the talk, why density functional theory, together with the approximations, which are usually made with DFT, has to be complemented with other many-body methods to attack such problems. And those acronyms here are basically such developments beyond DFT that I will come back to. Oops, that was interesting. That's not the end of the talk, okay? I just pressed the wrong button. Okay, wonderful. Okay, so, that point I already made, that it's really the methods and the algorithms that allow progress in this field. Okay, so to drive the point a little bit more, I've talked a lot about materials. I would like to get down to a little bit more simpler things and talk about simple models of interacting fermions. Not these complex materials, but somewhat simpler models. So it's really going through this jungle of oxides, rare earth, organic conductors, down to the beautiful idealized world of, models. And the simplest model in the field is written here. It is the so-called Hubbard model. So what is the Hubbard model? Well, if you'd asked me when I was a theoretical physics graduate student many years ago, what is a solid? I would probably have answered this. You know, it's a bunch of atoms. Since I didn't know very much the periodic table, I would have drawn hydrogen atoms with one electron in the 1s shell, because that's about all I knew. And I would have said, okay, these electrons circle around the nuclei, and once in a while they can jump, and that forms a band. Okay, that would have been my vision of a solid, and to many theoretical physics papers, I think this is still their vision of a solid. So the simplest model, which is based on this cartoon of a solid that captures the problem of interacting fermions, is the following thing. We have these electrons which hop from one atom to the other, and this is described by this term. So here we have a coupling constant, which is called the transfer integral, which takes an electron from this side and puts it on the other side. And so this is the kinetic energy part of the problem. If we only had this thing, we would just have a Bloch band. Okay? And here we have another term, which is a local interaction. So the interactions have been stripped to their basic principle. They just act on site in this Hamiltonian. And this term is basically telling you, you just cannot put two electrons on the same site without paying a price, which is U, which is an interaction constant. So this is the Hubbard model. Up to a few years ago, this model was really just a kind of spherical cow model, a little bit like the Ising model for magnetism. You know, it plays the same conceptual role in our field than the Ising model plays in StatMech or in magnetism. It's not a very realistic model for many things, but it is the simplest model that captures important phenomena that we want to understand, and we need tools to understand the physics of this model. So that's the conceptual status of the Hubbard model. But in the past about decade or so, this model changed status from being only a spherical cow to being something you can actually realize in the lab. And so I'm sure many of you have actually heard, or are even experts of the physics of ultra-cold atomic gases. Thanks to this field, there is really a new interface between condensed matter physics and quantum optics that have been developing, which allow to realize in the lab systems that are very well described by such simple Hamiltonian. So how does that work? Well, you probably all know about cooling atomic gases using various techniques. There's been 2 Nobel Prizes awarded for that. The first one to Chu Koentanuji and Bill Phillips for the cooling techniques in 1997, and more recently, a few years later, to the first people who realized the Bose-Einstein condensate using such cooling methods. Well, since then, these methods of creating very, very cold, which means slow, atomic gases have been combined with other techniques that were developed before for thermal gases, namely the possibility of trapping these atoms in optical potentials. So the idea is fairly simple. You actually create stationary waves with lasers, and you can actually, because of the induced dipole moment, you can actually trap an atom at the nodes or at the maxima, at the minima or the maxima of this wave. And you can do that in a 2-dimensional or 3-dimensional way, so that at the end of the day, what you get is a little bit like eggs, which are your atoms, into an egg box, which is your periodic potential created by light. And if you think of the analogy to a solid, your atoms or your eggs are like the electrons in the solid, and the periodic potential created by the light is like the periodic potential created by the ions, except that in this case, the ions don't move if your table is stable, and so you don't have phonons. Okay, it's really a realization of a perfect periodic perfect set of interacting quantum particles in a periodic potential without lattice vibrations. And if you have a deep enough lattice, you can actually separate the different bands and at the end of the day realize in the lab something which is very well described by a Hubbard model, if you use fermions, or Hubbard model for bosons, if you use bosons. And on top of that, these systems are very controllable because you can actually control the transfer integral T by changing the depth of the lattice. You can control U by atomic physics techniques called Feshbach resonances. So these systems are highly controllable systems, a bit of a condensed matter physicist's dream where you could be able to change the strength of the electron-electron interactions by just turning a knob. So that's really very nice. Okay, so phenomena, of course the energy scales, this is the beauty of physics. The energy scales are completely different between a real solid and these artificial solids. You know, the Fermi energy in a real solid will be something like an electron volt or a few electron volts, which is 10 to the 4 Kelvin. The Fermi energy we are talking about here are typically microkelvin, so we have 10 order of magnitudes between the two. The temperatures that are at hand would be like room temperature or perhaps, you know, if we do low temperature physics, millikelvin temperatures. Here we are talking about nanokelvins, the coldest temperature in the universe. But you know, it's the beauty of physics that despite considerably different energy scales and temperature scales, we can actually address the same physics questions in the two settings. And in fact, this field has made very beautiful progress, and we can now ask questions which are very similar between the field of materials with strong electron correlations and the field of ultra-cold atomic gases, especially in optical lattices. This is one of the early experiments that demonstrated that. These are bosons at the time, 2002. You had, I think, a seminar or colloquium recently by Emmanuel Bloch, so I'm sure you've seen similar things. So this is actually the realization in the lab of a mode transition between a state which is a superfluid, which is this state here, with a nice k equals 0 peak in the momentum distribution, to a state which is a bunch of localized bosons in these wells in which there is no quantum coherence and no k equals 0 momentum peak. Since then, many other things have been done. For example, transport has been studied. This is an example of a transport experiment that was realized a few years ago in the group of Esslinger. So one can create systems with these ultra-cold atomic gases that are very similar to what people do in mesoscopic physics. Left reservoir, right reservoir, some constriction which is laser engineered, and the ability to actually image the atomic distribution in situ of the system by microscopy techniques. And this is an example of the famous quantum quantization of the conductance in such a constriction as realized in one of these systems. So very, very similar to the early experiment in the 80s of the quantification of conductance in a quantum point contact. So these two fields are really coming together, and they force the theorists to actually improve their methods to treat this system with strong interaction between quantum particles, but they also offer us the possibility to test our computational methods versus experiments that are now done on much simpler and controllable systems, essentially realizing in the lab the model Hamiltonians that play the role of the simplest possible models in our field.
This goes beyond Hubbard, right?
Well, no, this is much below Hubbard. I mean, this is no interaction, right? This is just an electron. This is just a gas in a constriction, right? So in fact, in this experiment here, there is no interaction. So this is just an example of mesoscopic transport in a free atomic gas. Actually, there are subsequent papers, you see it's fairly recent, but there are subsequent papers of this one in which they start looking at how interactions in the reservoir affect the transport. Okay, so this is an example just to give you a feeling of where this field is as compared to the questions that condensed matter people may be interested in. This is the phase diagram of the Hubbard model at half filling, let's say in 3 dimensions. Okay, so this is temperature in unit of the transfer integral, interactions in unit of the transfer integral, and this model is fairly well understood in the case where there is 1 particle per site. It has basically 1 phases with magnetic Lagrange order, which is this phase here, which is an antiferromagnet, and it has here a crossover between an itinerant correlated Fermi liquid and a system which becomes gradually more and more incompressible, in which the particles are localized on site through some sort of crossover line. Okay, so people in this field like to call these ultra-cold atoms, but in fact, if you judge by those standards, they should really be called ultra-hot atoms, because, you know, just a few years ago, what people had managed to achieve with cooling techniques were temperatures of the order of the hopping integral, which really means, if you translate to the scales in the solid, something like thousands of Kelvin. Okay, so very, very hot matter by our standards in condensed matter physics. And it's only recently, in the last year or so, that cooling fermionic cooling techniques have achieved low enough temperatures that this sort of physics becomes accessible to these artificial systems. So the observation of the antiferromagnetic phase has now been realized by Markus Greiner and Immanuel Bloch, but it's only a recent achievement.
Can you make U negative?
You can make U negative, absolutely. And this is a whole field of people, you know, interested in looking at the crossover between the BCS regime of a superfluid and the regime where you form preformed pairs and look at them condensing. And it does, yeah, absolutely. So this has been mostly studied in the trap without a lattice, but people are also doing lattice experiments with negatives. Okay, so I'm obviously running out of time, but I want to actually answer the question of Pierre about acronyms. And to do that, I would like to make the point that actually what I would call the standard model of solid-state physics, coming back to the electronic materials, need to be reconsidered when you actually deal with these materials with strong correlations. So let me explain why. Well, here is the picture of Walter Cohn. I could have put, and I should have put here also, the picture of Pierre and the picture of Lushan. And when you think about a solid, and you open Ashcroft and Mermin, what you learn in chapter 1 is that a solid is made of atoms. And what you learn in chapter 2 is that you should only think of the electrons. And from chapter 2 to chapter 37, we only talk about electrons, right? So to a certain extent, and with due respect to DFT, this is what DFT does, density functional theory. It actually makes a very strong connection between the physics of a piece of material and the physics of an electron gas. And everything is expressed in terms of the local electronic density of this gas. Okay, so the point I want to make is that actually, if you want to think about these materials with strong electronic correlations, you need to keep the notion that, the very, mundane notion that solids, after all, are made of atoms, a little bit more into chapter 2, 3, 4, and 5, and so on. And let me explain why. Okay, so this is my cartoon picture, but now with a little bit of animation. What you see here is electrons that try to hop from one side to the other to form a Bloch band, but are prevented to do so by the strong on-site U, which prevents them to do so. And you would expect that indeed when U is small, you can form a metal and delocalize the electrons and have a Bloch band. But when U is large, this is actually not possible because the motion of the electrons is actually blocked by the repulsive interaction, then you'll have an insulator. This is called a Mott insulator. So if you want, this whole thing is a fight. Oops, where is this? Sorry, this will come later. I don't want to show all my jokes in the first slide. Okay? So, you know, this is the simplest possible form of insulator in which motion is just blocked by repulsive interactions. This is what happens in the Paris subway, right? At rush hours, also, I guess, in the New York subway. You have a filled car, everybody sits somewhere, you try to add a particle and somebody complains, and that is the strong U, okay? So you have an insulator, you have an incompressible system. It's very easy to explain to a kid, you know, why this is insulating. You just can't add a particle, and you can't move a particle within the car without hurting other passengers. If you try to explain to a kid what a band insulator is, destructive interference between Bloch waves, you know, Bragg reflections, and so on, good luck, okay? You won't succeed. So, you know, it's really the definition of Groucho Marx of an insulator, something like a 5-year-old kid can understand. So get me a 5-year-old kid. Okay. On the other hand, this also means that to understand this, you need to keep the notion of atoms. And in fact, you know, if you think about this problem, on short time scales, electrons remain localized in their atomic orbitals, and on long time scale, perhaps they will manage to delocalize. So this notion that there is atomic physics on short time scales and quasi-particles or delocalized physics on long time scales is not just a theoretical concept, it's actually something you see in spectroscopies. So let me show you an example here. This is a material which may appear complex to some of you who are not condensed matter physicists, but for somebody like me, is like the Drosophila of our field. It's a very simple transition metal oxide, and it's a metal. And if you look at the excitation spectrum of this metal, as measured by photoemission, what you see here as a function of energy, this is Fermi level, and this is below Fermi level, occupied states. What you see here is two kinds of excitations. Now, obviously, low energy excitations, which are the metallic quasi-particles, the delocalized aspect of the problem at low energy. But at high energy, there is here a satellite peak, which is very simple to interpret in terms of an atomic transition. It's basically taking an electron out of this vanadium D shell and removing it. So it's an extremely simple atomic physics transition, which is a little bit broadened because we are in the solid state context. However, if you do a bond structure calculation, which is based on the DFT formalism, plus, which is an exact formalism, plus approximations, unfortunately, that we have to do to the functional of the total electron density, so this is the state of the art for electronic structure calculations, what you find is that this excitation spectrum is actually lacking all these atomic transitions. And this is because you forgot the atoms. So what was very easy to explain to a 5-year-old child in terms of atomic transition is now lost because you've decided to focus only on the electrons. And furthermore, as you see here, the bandwidth or the kinetic energy available to this delocalized electron is about too large by a factor of 2 in this case. So this is the fact that to move an electron in a semi-filled subway car, well, the velocity of this electron will be reduced by the presence of the other particles, right? And this effect is underestimated by traditional state-of-the-art electronic structure calculation.
The dotted line.
The dotted line is DFT LDA.
Calculated.
Exactly, in the LDA approximation. Okay, so you are lacking a correct description of the quasi-particles, and you are lacking the high energy atomic light excitations. Okay, so how can you repair this problem? And that brings me to the acronym, DMFT, that Pierre was asking about. So it's a story of Mott versus Bloch, right? This guy wants to delocalize electrons. This guy wants to localize them. And in the most intricate and interesting cases, these two effects fight and coexist. And it's a question of energy scale. They coexist in the same system. Okay, so how can we overcome this? Well, what we have to do is to think in terms of atoms. And this is precisely what DMFT, which was this acronym for dynamical mean field theory, which is a theory that Gaby Kotler and myself started in the early 90s, not very far from here in Jersey. Paul alluded to my Princeton years, so this theory was to a large extent cooked up in Princeton and elaborated on previous ideas by Metzner and Volhard in Germany. So this theory says the following thing. Let us build for a solid, for a quantum solid, a kind of mean field theory which is very, very similar in spirit than what we do when we do classical statistical mechanics. So when we deal with the Ising model, what we do is we actually replace a whole lattice system by one site, which is, say, one spin, interacting with an effective bath, which is self-consistent and created by the rest of the solid. So this is exactly what DMFT does, except that what it does is that it retains one atom or one atomic shell. So we keep the atom and all its complicated many-body set of states from step one. And the exchange of electrons between these atoms and all the atoms in the rest of the solid is viewed as the exchange of electrons between this atom and an effective medium. But this effective medium is, of course, built out of all the other atoms. So it's a self-consistent effective medium. So it's really the generalization to the quantum many-body world of the very well-established idea of a mean field theory in classical stat mech. Okay. The only catch, of course, is that I'll pass on the technical details, but the only catch is that the local problem we have to solve is, of course, much more complex than just a spin in a Weiss field. It's actually an atomic shell interacting with a bath of electrons and exchanging electrons. So it is a many-body problem in itself, which belongs to a broad class of many-body problems, which we can call quantum impurity problems, like Kondo models, for example. So we need computational tools to solve this problem, and this actually is what brought me from pure theoretical physics into more the computational world. As far as I'm concerned, we need tools to solve this atom in a bath problem. And we need, of course, efficient algorithms to do this fully self-consistently, first for a model, like the spherical cow Hubbard model, and then later on, as we have done in the past 10 or 15 years, for a real solid, combining these methods with density functional theory. Okay, so one of the really nice things, I'll skip on this thing, so one of the early achievements of these methods has been to describe this phenomenon of a transition between a metal and a Mott insulator. And the two types of excitations in this problem on equal footing, and to provide a very detailed theory of this transition. So this happened early on in the early 90s. Here what you see is this excitation spectrum. It's a cartoon, but it reflects real simulations, where you see how you evolve from a system which is just a Bloch band, this is the density of states of a Bloch band, into an excitation spectrum that has narrow bandwidth quasiparticles at low energy, plus these atomic satellites at higher energy, and at some point the system becomes an insulator, the quasiparticles disappear. So that was an early success of these approaches. So to a certain extent, this is a step towards the program of Dirac, because we've managed to bring this formidable problem of computing 10 to the 23 electrons interacting together into a problem with some approximation which becomes manageable. The reason it becomes manageable is because this local problem of one atomic shell coupled to a bath, if you treat it by Monte Carlo algorithm, for example, is free of the minus sign problems I was describing before, and you can really solve this problem on the computer very accurately. Okay, just to cut a long story short, and because it's already past the deadline, let me just mention that there's been a huge effort between the early 90s and basically now to actually make a happy marriage between these DMFT methods and the density functional theory methods, which are very important to take into account structural and chemical realism in solids. And this has resulted into a whole scheme that allows us to go from these spherical cow models to treating a real solid with these methods. This is an example. So I mentioned already this material. I mentioned its photoemission spectrum. And I will cut a long story short and just show you a comparison between the calculated photoemission spectrum with these methods, which are the plain lines here, and the experimental data, which are the data. And you see that these methods actually do a reasonably good job at predicting both the quasi-particle excitations and the Hubbard satellites accurately. And importantly, the transfers of spectral weight that are seen in all the spectroscopies when you change a parameter like pressure or temperature. And these two kind of states actually communicate, and describing these transfers of spectral weight is really important. Okay, so I had many other things I wanted to tell you, but just to conclude the talk, let me just highlight a couple of new directions and I'll shut up. So I've taken you into the jungle of materials, the idealized world of simple models. Obviously, what we would like to do is not only understand these materials, but actually make them do what we'd like them to do. And I mentioned the importance of control. They have very complex phase diagram, and we want to channel the material to do one thing and not the other. So how do we do that? Well, there are different ways to do that. One of the really beautiful way that has been very much developed in the past few years. So there are all the tools of the chemist, of course, doing substitutions, using the tools of the physicist, like pressure and strain and so on. But there are new tools to do that. And there are basically two directions, which are a little bit more novel, which allow to do that. One is to actually engineer artificial materials through controlled heterostructures, growth in a controlled way, and perhaps combining different materials together. So that's one thing. And the other thing is actually a more recent field in which one tries to drive a system out of equilibrium with carefully shaped laser pulses. So let me just illustrate this very briefly. I already showed this picture. This field started in the early 2000s with the first elaboration of controlled heterostructures of such transition metal oxides, and many, many things have been seen in this field since then, including superconductivity in the LAO-STO interface, for example. So this is an illustration of the second route to control, which is the following thing. The fact that the energy landscape of these materials is complex and there are many phases also suggests that there may be neighboring phases which are not really stable at equilibrium, but which may be separated from the true equilibrium phase by a small energy difference. And the idea is, can we actually, by shooting on this material, a carefully engineered laser pulse, for example, whose energy is resonating with a specific structural mode of the material, can we actually change the structure into a new structure which would not be the stable equilibrium structure and which would have a different electronic functionality? And so this has been demonstrated in the lab. The pioneer of this field is actually Andrea Cavalieri, now in Hamburg. And this is an example where this nickel oxide that I mentioned before is actually grown on a substrate when comes with a mid-infrared laser pulse, femtosecond laser pulse, which is resonant with one of the structural modes of the substrate, and that actually changes transiently the structure, the crystal structure of the material, into a new structure which switches the material from a magnetic to a non-magnetic state. Okay, so this is really the frontier of the field, is not only trying to understand these materials, but actually trying to control them into doing things that we want them to do. Okay, so that's it. Thank you for your attention. And I kept this very broad, of course, but I'm happy to enter into the technical details at a later stage.
Sure.
I didn't understand. In terms of computational law, what is the bigger computational problem? To solve one atom in a bath or to do the self-consistency?
Definitely, okay, definitely to solve one atom in a bath. Okay? Because the self-consistency is easy. It's actually just, it's a problem which doesn't mix the different energy scales. It's a problem which is frequency by frequency. So that's an easy problem. The problem of one atomic shell, we can't even do one atom these days. We can only do one atomic shell. I cheated a little bit, because this is a colloquium. I cheated a little bit when I said that we retain the whole atom. We can't do that. It's impossible computationally. We retain the states that are actually the strongly correlated states of the solid. So we retain a D shell or an F shell, just one shell. So just to give you an idea, if we are interested in the Hubbard model, which is just one orbital per atom, right? Then no problem. We have many, many algorithms that now do that. Many of them have been tailor-developed to do DMFT. Now, if we go to a transition metal oxide, we're going to retain a D shell. A D shell has 5 orbitals, right? L equal 2, 2L plus 1, 5 orbitals. Okay? So 5 orbitals plus spin, which is 10 states, right? 10 degrees of freedom, coupled to a bath, right? That we can handle. But we can handle it when the system has sufficiently high crystalline symmetries for a reason that I don't have time to discuss. When we go from a D shell to an F shell, that becomes difficult. Okay? On top of that, most of the calculational schemes that we have by now for D shell or F shells are Monte Carlo based, which means that they all lived in imaginary time, right? We do a Vic rotation. Okay? So spectroscopists don't like imaginary time, right? They make real frequency measurements, and this is the infamous problem of analytic continuation, right? Ideally, we would like real frequency and perhaps real-time solvers to do non-equilibrium that are able to handle a D or an F shell. Nobody is there yet that I know of.
When you say, you know, at low energies you have the localized states.
The opposite. At low energy we have delocalized. At high energy we have localized.
Delocalized states.
Yeah.
And at high energy you have localized states.
Yes.
Low and high are a factor of 2 apart.
Yeah.
So.
Well, factor of 2, no, let me qualify that, okay? So, in the example I showed you, this atomic transition, you know, which requires sort of a localized vision of the atom, is at about 1.5 eV binding energy. The real quasiparticles, right, as you know very, very well, are only existing at really low energy near Fermi level, right? So it's not factor of 2, it's actually several orders of magnitude, right? If I take, just to quantify that, let me take another oxide like strontium-2 or uranium-4. The Fermi liquid coherence scale in this material is 25 Kelvin. The Hubbard band is at, let's say, 1 eV or 2 eV. Okay? So between the two, there are 3 orders of magnitude.
But I'm naive, but I was looking at your picture.
Yes.
And you pointed to the peak.
Yes.
And then you pointed to the
Yes.
smaller.
No, I exactly understand your question. The thing I was showing is a total momentum integrated density of states. Okay, so what you're telling me is that the bandwidth of the low energy quasiparticles was about half an eV, or 1 eV, right? And the atomic transition is about 1.5 eV. This is your factor of 2. Okay? But this does not mean that if I look at the states that are 0.5 eV away from Fermi level, they are well described by long-lived Landau Fermi liquid quasiparticles. If you want long-lived Landau Fermi liquid quasiparticles, you have to go to much, much lower energy. And these two scales, the scales below which you have long-lived Landau quasiparticles and the atomic transition, typically can differ by factor of 100 to 1,000. So there is a separation of energy scales.
And your illustration was somehow just
it's a colloquium pair, yeah. Yeah, but we can calculate this. You know, in strontium 2 ruthenium 04, I can show you DMFT calculations for this material that show that indeed you lose the Landau quasiparticle form of the quasiparticle scattering rate at 20K, right? While you completely lose any notion of coherent quasiparticle excitations much higher at like 1,000 Kelvin. So there is really a separation of energy scales. This is actually something we've learned from these theories. I think, you know, there was a big overestimate of the range of validity in energy of concepts like Landau quasiparticles in the theory textbooks of the 70s, okay? And in fact, when you really try to estimate where the Landau Fermi liquid concept really applies, this is only very low energy, and this is seen in experiments.
Okay, are there any urgent questions? I think you've got to run, so we should go.
No, not run, but
ask further questions over wine and cheese
yeah.
across the street. So let's thank.
Thank you very much.